Good afternoon. I'm super excited about this video today. So what we're going to be going over today is called gradient boosting. So previously, if you haven't watched, in the previous video we talked about decision trees. This is decision trees on steroids, right? One of the most transformative models that have been discovered and has come into at least the Kaggle industry, and then has been able to create models such as XGBoost, which you'll see as one of the most predominantly used classifying models that are out there right now. With that said, I want you to picture with me a track race. I'm running. I then pass the baton off to my teammate. They then continue running, and they pass the baton off to our other teammate. They then continue running, pass the baton off to our other teammate until we finally have finished the race. Right? Think of gradient boost the exact same way, right? So what gradient boost is doing is it's going to take multiple models in what is called an ensemble. So it's a form of ensemble modeling, which means that there's multiple models being built in sequential order. So this first model is going to get created. It's going to be a decision tree, which then presents a loss function, or the loss error. Let's say that loss function is 0.8, right? So 80% of loss. Our next model that comes across is going to take that 0.8 and try and correct the 0.8. So it's going to try to correct the model based off the loss error. It's then going to present an error to its teammate, for the same analogy used as the track analogy I used at the beginning. Right? So all the way until we've minimized the loss function. What we can think about with loss function, and whenever we say gradient descent or gradient boost, or we think of this gradient, what is this? I want you to think of two stairs sets coming together. So let's see if I can fit my hand. There we go. So two stair sets coming together, right? One is we start at the beginning, which is at the very top of the stairs. And as we go down the stairs, we are minimizing the loss function, right? All the way until we get to the very bottom of the stairs. Now, we don't want to go back up the stairs. We want to stay at the bottom, right? We've minimized the loss function. So we know that the error is low. The loss, or the room for error margin, is low. We don't want to go back up the stairs in either direction, right? If we start going up the other direction, that's bad. If we start going up the opposite direction where we came from, that's also bad, right? So gradient boost will work, present models, keep building these models until we've minimized that loss error, right? So that is the whole concept of gradient boost, gradient descent. That's where we're headed, right? So with that said, what we've done here is we've taken a data set that represents the employees who work from home and get burnt out. So these are attributes or features that represent getting burnt out and what drives that, right? So we have items in this data set like day type. Is it weekend or weekday? How many hours? Screen time, meeting counts per day, how many breaks were taken, how much do they work after hours? So you can see this person worked 1 hour after work. How much sleep do they receive each night? What does their completion rate look like? Their burnout score. And then here on the very end, our target is the burnout risk. So are they high, medium, or low based off their attributes is what we're looking for. Right? So at the very beginning, at the top, you can see we're bringing in our libraries. So we bring in pandas, NumPy. We bring in our metrics from scikit-learn. We bring in our train test split, our GradientBoostingClassifier, our one-hot encoder, our pipeline, our column transformer. Then we bring in some of our metrics, classification report, confusion matrix display, and ROC AUC score. Then we bring in items like matplotlib for our EDA, where we're doing our univariate analysis. We use missing no. I do not believe I end up actually using that here. tend to use it, bring it in so we can see what columns are missing, if there's any missing. In this case, there are not any from what I saw on the Kaggle side. So let's get into it. We start out, we're reading the data frame and presenting the top rows, as we just discussed. Then we're declaring our variables, so our target is going to be our burnout risk. And then we are declaring our y-axis, which is going to be our burnout risk column. Then we're declaring our x, so our x is going to be our original data frame, and we're going to drop our target column, and then we're also going to drop the user ID column. So user ID column cannot be used to predict, right? It's just an identifier. It just identifies the employee, but doesn't necessarily say this is a predictive feature. It's not something like how old is the employee, how long have they worked there, what's their tenure like. Nothing like that. It's literally just an identifier. Think of it like another social, right? So we're going to get into describing the data frame for our EDA stage. So first we're going to split into our categories and our numerical columns. So we have our categorical columns and we have our continuous variables being split out here. For our categorical columns, we're doing value counts, so looking at the frequency of each category. So here, for instance, we can see that for our first category column, which is day type, there were 924 records showing on the weekend, 876 for weekday. And then for our target column specifically, we look to be imbalanced, right? We'll get to that in a second and how to handle that. But we look to be imbalanced. So for our category of low, we have 1,500 records. For our category of medium, we have 253. For our category of high, we only have 20, right? So quite the imbalance, where there's more packed into one category versus another, right? If we're not careful, that can cause something like overfit towards our training set or underfit towards our training set and be more predictable towards our test. Right? Now we're going to loop through and plot our distribution for our numerical columns. And what we're doing here, if we take a step back, what we're doing here is we're exploring our data, making sure that it's in a condition that's fit to go into our model. So we don't have a lot of skewness, right? We don't have everything packed into, say, work hours at 12. Everybody's working work hours of 12 per day. We know that's not typical, so we don't want to put that into our model. If that's something that's going to skew our numbers, make our model see visions that are not accurate whenever we bring in more data later towards our model. Right? So we can see here for our distribution of work hours, we have a bimodal distribution. So we have this hump here, and then we have another hump. For our screen time hours, we have 2 again there. And that's just telling us where the majority of our records are located. Right? Here for distribution of meetings counts, we can see we slightly skew to the left-hand side, where we have more meetings being in this 1 range per day. The distribution of breaks taken, you can see there's no real clear pattern to that. It's just kind of all over. And then distribution of after work hours, most people are packed into 0, but we do get 1 for some. And this is what we see as normal distribution. So for sleep hours, for the most part, everybody's right around this 7 to 8 range, right? With more being more towards those 6 hours and 45 minutes in that to 7, right? And so to keep on going, we'll not run through all of those. We're going to split our data set into our train test split, right? Where we're packing 80% towards our train data and 20% towards our test. We're giving it a random state 42, and we're listing this as stratify equal y. So what this does is it helps to handle the class imbalance. So like how we talked about at the top, where we had this class imbalance of low, medium, high for our burnout risk. Here with this stratify equals y, this helps to handle that whenever we do our split. Right? Next, we're going to create our preprocessor, where our column transformer is going to be our framework, if you will, that handles our categorical columns getting treated with a one-hot encoding, and our numerical values being treated as pass-through. We're not going to necessarily do anything with those. But our one-hot encoding, where we have weekday and weekend, if it's not weekday, it's weekend. So we'll have a column that says weekend underscore true, something to that effect, and it's going to end up being a true false, where if it's not true, then it's a weekday, right? And that's how we can assess that. Then we're going to get into creating our gradient boost classifier. So here we've got gradient boost classifier, our random state of 42. We're going to give this a number of estimators of 300 and a alerting rate of 0.05, and then a maximum depth of 3. So again, kind of like whenever we talked in a previous video about our decision trees, and our decision tree has multiple layers, our gradient boost classifier is going to have 3 layers here, right? And that's what that max depth is representative of. We then get towards where we create our pipeline. So our pipeline takes into consideration our preprocessor and our gradient boost classifier. So our model is composed of a pipeline that goes through 2 steps, our preprocess and our gradient boost. Now we're going to go ahead and fit our model to our train set. And you can see here, in using this pipeline and our column transformer and putting these steps into a pipeline, we're able to get more of a visual of what this looks like. So that's what we're seeing here, is our pipeline is composed of a column transformer that takes our categorical variables, our numerical variables, and handles those, and then moves towards our gradient boost classifier with the outputs. Now we're going to use the model to predict on our unseen data, or our X-test, so our test set, and we're going to create our predictions. So our Y prediction comes from our model predicting on our X set, or on our test set. Right? Now we're going to assess our model through the classification report. Right? So at the top we brought in our classification report from scikit-learn, and here what we can see is that when the model predicts high for the risk, how often is it correct is what precision is telling us. So 80% of the time it's correct. For low, whenever it predicts low, 100% of the time it's correct. When it predicts medium, 100% of the time it's correct. Right? And that's what this is telling us. Now, what our recall is telling us is that of all the true cases, how many did we actually catch? Right? So for high, we caught 100%. For low, we caught 100%, and for medium, we caught 98%. Right? Now, moving on towards how we analyze this further, we're going to create a confusion matrix. So here you can see we're taking confusion matrix, passing in our Y test and our Y predictions. And then we're passing in our labels and our model classes. Then we're passing in our confusion matrix into our confusion matrix display. Again, all of this was brought up at the top, and this is where this really becomes powerful for analyzing the performance of our classifier. Okay. If we go back down, okay, now we're just going to plot that. We're going to take what we just built here, our confusion matrix display, and we're going to plot it so that we can visualize it. So we're saying we're putting dot plot at the end, and then we're giving a title here, and then saying show. Now let's take a look at this here. If we zoom in, we can see that 305 predictions were accurately predicted as low, low. 50 predictions were predicted as medium, medium. 1 prediction was predicted as high, medium. And then 4 predictions were predicted at high, high. Right? So of all our predictions, only 1 was technically inaccurate compared to the truth, right? And that's our high that we predicted, and it should have been medium, right? So we get this 1 here. Now we're going to build our ROC AUC curve, and just a reminder, what this is it's going to tell us as the number results closer towards 1, however close it is towards 1, tells us the better performing that it is. So our goal is to be as close to 1 as possible. Right? So here we have y, and we say probability, and then we are saying if the number of our model classes are equal to 2, then we're going to perform this way. So AUC is going to be ROC AUC curve, our score with our y test, y probability, and then this function here for our indexing, and then for our else, we're going to say AUC equals ROC score, our y test, our y probability, and our multi-class we're listing as OVR. So then we're going to print this out, and as we can see a result, we have a result of 99.95. That's pretty high and as close to you can get to 100%, right? So that one value would tell us 100. Right? So with that said, that is the end of this video for Gradient Boost Classifier. Thanks for joining me. I'm going to be placing this Jupyter notebook into a GitHub repository and placing that repository link in the description of this video.